Okay, in this video we're going to talk about the Affine Cipher. I'm going to go ahead and write that down. The Affine Cipher. The Affine Cipher uses sort of like a linear equation to encode something, okay? So let's do this in blue here. So what I'm going to do is I'm going to take, so when you do cryptography, I'm going to remind you, you have a plain text, which is the message you want to send. You will encrypt the message. This pin's a little big, yeah, maybe not. And create what is called a ciphertext. So your plain text is a message you want to send. If you encrypt it, you'll get a ciphertext. And then that will be, so this is the encryption. And then you'll have to decrypt the message to read it. And this will be done somewhere else to the person you're sending it to. So the whole idea of cryptography is to encrypt a message. That way, if somebody else gets the message at this point, they won't be able to understand what it says. Okay? So very important for lots of practical applications. Okay. But here's how this works. So if I have a plain text, there's the numerical alphabet right here. So we say numerical alphabet. This is English alphabet with every letter assigned a number. And it goes from 0 to 25. So this whole operation will be done mod 26. If you don't know what a modulo is, you need to look it up because this is a very important for cryptography, cryptographic systems. Okay, so here's what we're going to do. We're going to take, we're going to get a key. So we're going to take, here's how this works. We have an equation that's going to be y equals alpha x plus beta. And my key, which is what I use to encrypt the message. So if somebody gets a hold of the key, they'll be able to read any message you have if they know what the key is alpha comma beta. These two things make up your key. And one of the requirements is that the greatest common divisor between alpha and 26, which is the modulo we're doing, has to equal 1. And I'll explain why later on, but this is the important part. I'll also tell you this, that alpha and beta can be, well, technically they can be any value between 0 and 25. Okay, they can be any of these, except only really beta can, because alpha, which has to satisfy this condition, if all the values between 0 and 25, out of all of those, only, so when I say greatest common divisor, it's the same thing as greatest common factor. So the greatest common factor of alpha and 26 needs to equal 1. And out of between 0 and 25, there's only 12 possibilities where that's true. Okay, so you could say that alpha has 12 possible values, and beta will have 25 possible values, 26 possible values from 0 to 25. So there's actually going to be 312 possible keys to use if you're using an Affine Cipher. So the reason this isn't really used in the age of computing is because a computer can actually test all 312 possible keys with any plain text or ciphertext very quickly. So this was a very useful thing before the age of computers, because testing all 312 keys is rather impractical, and nobody could actually break the message very easily. It's possible, but it would be very tedious. But with computer systems that can do calculations very quickly, this can be done very, very fast. So Affine ciphers are not typically practical anymore, but they once upon a time they could have had a use. So here's the deal though, in these mathematical things. So what I'm going to have is a plain text message, and I'm going to make the message, just call it bread. That's a word I'm going to encrypt. This is my plain text. Okay, and we're going to have to translate this into its numerical form. So we have to convert all these letters into the numbers that correspond to them. So I say 1 is for B, R is going to be a 17, and E is going to be a 4, A is going to be a 0, and D is going to be a 3. So what this is the plain text. This is my domain. This is my X values. My X values that are all going to go into here. So this is your plain text for X, and what's going to come out is your ciphertext. This is actually, I'll call this Y is your ciphertext right here. So we'll say Y is my ciphertext, X is my plain text. Okay, so we need to get some Y values coming out of here. So I'm going to pick an alpha and a beta, and I'm going to pick 7 for alpha, and my beta I'm going to make it 2. The reason I'm picking 7 is because I know the greatest common divisor between 7 and 26 is 1. So prime numbers work out quite nicely. They don't have to be prime, but primes seem to work. So there we go. So we're going to do this. We're going to encrypt this message. So here's the equation. Y is going to equal 7 times x plus 2. Since my alpha and my beta are 7 and 2. I'm going to feed into that equation all of these values. Okay, so here's what I'm going to do. I'm going to say, okay, this is going to be 7 times 1 plus 2. It's going to be 7 times 17 plus 2. This is going to be 7 times 4 plus 2. 7 times 0 plus 2. And 7 times 3 plus 2. Cool. Okay, so we're going to get numbers out of these calculations. You need to do them all. So 7 times 1 is 7 plus 2 is 9. It's going to be 70 and 49, which is 119 plus 2. So this is going to be 121. This is going to be 30. Oops, what happened to my marker? This is going to be 30 right here. 28 plus 2 is going to be 0. It's going to be 2, actually. 0 plus 2, which is 2. This will be 21 plus 2, which will be 23. So these are the numbers I'm getting out. But the problem with these is these do not, if you look at these numbers, some of them like 121 and 30, they won't correspond to this alphabet. So the problem here is we have to now mod them 26 so that they will correspond to the alphabet. Okay, so we say mod 26. So here's the part that I guess the modulo part is actually the hardest part of this cryptography business, in my opinion, because the rest of it is pretty straightforward. But here's what I'm going to do. I'm going to pick a number like 121. I'm going to mod it 26. I'm going to show you how to do that. So what I do is I say n is equal to q times the modulus, which is m, plus a remainder, r. So this 121 is my n value. This is going to be q, my mod, which is mod 26. We're going to do mod 26 because we're using the English alphabet and we're corresponding all of our letters with those numbers. There's 26 possibilities, 0 to 25. So when I say mod 26, the values that are possible for mod 26 are 0 to 25, not 26 itself, but all the numbers that come before it that are 0 or positive. Okay, so this is going to be mod 26 plus r. And here's what I got here. So this value, q times 26, needs to be less than 121, but it has to be as close to it as possible. So what I like to do is I like to divide 121 by 26. So I'll say, what is 121 divided by 26? And that's going to be 4.65. I'll just take the integer part. I'll chop off the decimal, keep the integer part, and say, okay, what is 4 times 26? So when I found this 4, this integer part is my q. So I'm going to say, what is 4 times 26? That's going to be, so this is 4, which is my q, times 26 plus r. And I just told you that this is 104. 4 times 26. So what I have now is I have to find the remainder, and that'll be my mod. Okay, so 121 minus 4. That's really the question, is 121 minus 104, right? 121 minus 104. So that answer is going to be 17. So what I can now say is that 121 is actually equal to 17 mod 26. So 17 is actually the number I'm going to use as the translation for the ciphertext. Now, if I did this process with any number that's less than 26, like 9, 2, or 23, it would just be the same thing. It would be 9 mod 26. And this would be 2 mod 26. It wouldn't change. But anything over 26 would change. So this is going to be 23 mod 26, and so forth. Okay. And this right here, 30. What you could also do is subtract 26. If I did that, it's like saying 30 is equal to 1 times 26. I'm actually just going to do this whole thing now, plus r. So that means that r would equal 4. That's your remainder, okay? So this is congruent, we say, to mod 4 mod 26. So these numbers right here make up my ciphertext. So my y values, which are my cipher, that comes out, my ciphertext will be 9, 17, 4, 2, 23. Okay, so this is my plain text, this is my ciphertext. It's encrypted now, right? So if I actually want to make an actual word message, 9, 17, 4, let's see, 9, a new letter message. So let's do this. 9 is going to be a J. So I got 17, which is R, 4, which is E, 2, which is C, and 23, which is X. So this word, which is bread, I've encrypted, and now it says this, which is even in word. Okay, so somebody that intercepts your message will get that, and they will have no idea what it says, theoretically, unless they can crack the encryption. All right, so that's how you encrypt it. That's pretty straightforward. That's the encryption process for an Affine cipher. The decryption process is in most cases, the harder part. So what we're going to try to do is go backwards, okay? So here's my encryption process, which is y equals alpha x plus beta. That's the equation we're going to use. And now we're going to try to reverse it to solve for x again, go backwards. So what this means now is that alpha x is going to equal y minus beta. And x, I can get rid of this alpha by taking its inverse. So if I were to multiply both sides by the inverse of alpha, okay, that's what I would get right here. This would go to 1. Anything times its inverse would equal 1. So x is actually equal to the alpha inverse times y minus beta. This is my decryption process right here. The hard part of this whole thing, really the only challenging part, is finding this inverse. Okay, because technically if I were to say alpha were 7, if I were to say alpha, keep hitting that screen, alpha is 7, then you would think, okay, the alpha inverse has to be 1 over 7, right? Because what we're trying to say is that alpha times its inverse will always equal 1. That's what it means to be an inverse. It just undoes it. And 7 times 1 over 7 will equal 1. The problem with using 1 over 7, shouldn't erase that, with using 1 over 7 is that there is no mod for that. Mod 26. You can't just say a fraction 1 over 7. It's not going to work. So what we're going to have to do is to find this inverse, we're going to have to find the inverse mod of 1 over 7. And that's the hard part, because you have to use what is called the Euclidean algorithm to do this. And I'm going to walk you through it, but this is when I was learning how to do this, and it took me, I looked at this for, I don't know, a couple hours. Oop, I got a message from somebody. I was looking at this for a couple of hours, and then I figured it out. And when I say a couple of hours, I was doing the Hill cipher, and it took me a couple of hours to figure that out. And then once I figured that out, actually all the other ciphers are pretty simple. So here's what I want to say here. So here's what we're going to do. We're going to find the inverse modulo, which is the hard part. And I posted some YouTube videos on how to do that on this whole process. But here's what I'm going to do. I'm going to say that 7 times something is equal to 1 mod 26. When I say 7 something, this is 7 times something else is equal to 1 mod 26 is what I'm saying. Okay? And now what I'm going to try to find is what that is, what this x is. Okay, that's the inverse modulo. It's what this inverse is. Okay, so here's the deal. If I do this, that means x is going to equal, when I divide both sides by 7, it's going to equal the inverse of 7 mod 26. And I have to find the inverse of 7. So here's what we're going to do. We're going to use what is called the Euclidean algorithm. Okay, and here's how we're going to do this. The algorithm does this. Let's change this color to red. Okay, we're going to take the mod first and set it equal to. We're going to take the inverse of the inverse of 7, which will just be 7. All right, and then we're going to say multiply 7 by something plus something else. Okay, this is what this is equal to. So this process here we can walk through. I'm going to use a different color. We're going to say 7 times what will give me a number that's less than 26, but not, but still closer to it, as closest to it as I can possibly get. So this is going to be a 3, because 7 times 3 is 21. So this remainder will be a 5, okay? 7 times 3 plus 5 will give you 26. This is true. All right. And then the algorithm says to take this 7 right here, right? And we're going to move it to where that 26 was. This is going to be 7 now. And this 5 on the end is going to move where the 7 used to be. Okay, so this is 5 times something plus something now. And this keeps shifting over and over until I'm looking for a 1 right here. Okay, and this is a great thing because I'm going to explain something here in a second. So 5 times what gives you 7? That's going to be 5 times 1, and then plus 2. So now we're going to shift the 5 where the 7 used to be, and this 2 will shift where the 5 used to be. I'm going to say, well, this is 5 is equal to 2 times 2 plus 1. And now that I have plus 1. I don't know why I put that. Ooh, that's not an eraser. Figuring out this tablet. Let's do this. I'll eventually figure it out. Plus 1. Okay, so this 1 right here is your remainder here. So what you've just proven really is that the greatest common divisor between 7 and 26 is equal to 1. And that's what this number is right here. The reason this is true, the reason we have to have the greatest common divisor, which is a common factor between 7 and 26 is 1, is because if you had other factors besides 1 that are common to 26, the greatest common one, you would have several different plain texts for a single ciphertext. So when I went back to decrypt this message, right, if I were to do that, I would have several possible messages coming out when I only want one single message. That's the problem. I don't want to have several different possible messages or interpretations for this when I decrypt it, and that's what would happen if this isn't true. I only want one interpretation when I'm unlocking it with the key. So that's how that works. So here's the deal. So now we have to actually we haven't found the inverse mod yet. We have to use what is called the extended Euclidean algorithm now. And this, in my opinion, is the hardest part of the whole cryptographic process. The rest of it's not so bad. Okay, so what I'm going to do now is, this is actually pretty interesting, is I'm going to take this equation and I'm going to solve it for what the number on the end right here. So I'm going to say 1 is equal to 5. I'm going to subtract 2 times 2 from both sides, but do not distribute. Oh, man. Do not distribute this. Do not distribute this, okay? So we're going to say 5. I'm going to say plus 2 times negative 2. If I subtract 2 times 2, it's the same thing as saying 2 times negative 2. I'm going to write it like that. So this is the same thing as this, is what I'm saying. Okay? And we're going to do the same thing with the equation above it. We're going to say, take the number on the end and set it equal to 7 plus 5 times negative 1. That's the same thing as this right here. Okay? And here's the reason I'm doing this, because now I have something here. What I have here is I have 2 is equal to all this. And I'm going to plug all of this into this 2 right here because it's equal to 2. This is the process. So do not distribute this, because if you do, you can't do this. We're going to take this and plug it into that 2, into the top equation. So now 1 will equal 5 plus 7 plus 5 times 1. It's important you don't distribute things, or multiply things through anyway. You can distribute stuff, but you can't multiply it through, times negative 2. Okay, so here's what I'm going to do. I'm going to distribute this negative 2, but I'm not going to multiply it through. I'm going to say, okay, 1 is equal to 5 plus 7 times negative 2. So I distribute, but I actually don't multiply it through. 7 times negative 2. And then plus, I have a 5. And here I can actually multiply through. Negative 2 times negative 1 is a positive 2. I'm retaining the 5. Oh my goodness, why does it keep flipping to an eraser? Okay. I'm retaining the 5 and I'm retaining the 7. Why am I doing this? Because I have a 5 right here. Okay, so what I have here is I have a 5 here and a 5 times 2. So there's 1 5 and 2 5s here. So this is now equal to 5 times 3, really, when I combine this and this, plus 7 times negative 2. Okay, that's what I want. Okay, I'm going to take the top equation right here, and I'm going to do the same thing. I'm going to convert it and solve it for 5. I'm going to solve it for that 5 right there. So I'm going to say 5, this is from the top equation, is equal to, you just keep working all the equations back up to the top. and solve for the end, which is the remainder part. 5 is going to equal 26. If I subtract 7 times 3, it's the same thing as adding 7 times negative 3. And that's what I'm going to say that is. This is equal to 5. And because it's equal to 5, I can plug this in right here for the 5. So now I have this. I have 1. So this top equation is now going to equal 1. So 1 equals, this is going to be 26 plus 7 times negative 3. All of that times 3. We're plugging in for this 5 only. Times 3 plus 7 times negative 2. I'll distribute this 3, but don't multiply it through. So this is going to be 3 times 26, which is 26 times 3. I got 7. I'm going to multiply the negative 3 and the 3. That's going to give me negative 9. I'm keeping the 7. That's my alpha still, remember? Plus 7 times negative 2. So if I reduce this is 26 times 3. I got negative 9 times 7 and negative 2 times 7. So it's like saying plus 7 times negative 11. That's what I really have now. Because negative 9 plus negative 2 is negative 11. Now this is great, because what this now means is that 26 times 3 plus 7 times negative 11 is equal to 1 mod 26. All of this is being done in mod 26. If you have any multiple of 26, which is 26 times 3, mod 26, that's going to equal 0. So you can ignore that part. This is the 7, and this is the inverse. What I'm saying is this is 7 times the 7. The inverse of 7 is going to equal 1. So I now know that negative 11 would be the inverse, but I still have to mod it 26. So negative 11 is what I'm looking for. It's just not the answer because I can't have a negative answer. And so here's what I'm going to have to do. If it were positive 11, I could leave it. If it's less than 26, I could leave it. But now this is a negative 11. I have to convert it to a positive modulo for this particular example. So this won't always happen, but it's happening for me. So here's what I'm going to do. I'm going to say, again, the process n equals q times m plus r, which I've already talked about. Okay, here's what's going to happen. This m is my 26, that's the mod. N is my negative 11. And this is q plus r. This needs to be less than this. This is always less than this. And this is negative, so this has to be more negative. Okay? So if I just multiply 26 by negative 1, that'll make it automatically more negative than negative 11. And the whole reason for this is I'm trying to get a positive value for r. So here's what's going to happen. Now I have negative 11 is equal to negative 26 plus r. R is going to be positive here. Now r is going to equal 15. This is what I was after. This is actually my alpha inverse. So alpha inverse is equal to 15 mod 26. This is my inverse. You can't use 1 over 7, but this is the equivalent mod 26 that you would have. This is 15. And that's what I'm going to use. So this is going to go back up to here, where this part right here, this is going to be a 15. Y minus beta. Now we can actually figure out what x is, which is my plain text going backwards. So 15 times y minus beta is my decryption process. What is beta again? Beta I already told you was 2. Okay, I told you that from the very beginning, that beta was 2. Somewhere right here, beta was 2. Okay, so let's take a look at my y values. What were they? Encrypted, it was JR ECX, which is 9, 17, 4, 2, and 23. 9, 17, 4, 2, and 23. Okay, so go back. Y equals 9, 17, 4, 2, and 23. And now I'm trying to find the x's. So this is my cipher still. And this is my plain text right here. So my y is my cipher. This is my cipher. And I'm going to plug in all of these values into this y. And decrypt with this process. So this is going to be 15 times 9 minus 2 And we'll just keep doing this all the way through. 15 times the next value, which is 17, minus 2. 15 times 4, minus 2. 15 times 2, minus 2. 15 times 23, minus 2. And so forth. So we'll solve all these algebraically. So 9 minus 2 is 7 times 15. That's 70 and 35. So that's 105. 17 minus 2 is 15. So 17 minus 2 is 15. 15 times 15. So this is going to be 225. This is going to be 2 times 15, which is 30. This will be 0. This will be 21 times 15. Okay, you're thinking, okay, that's my answer then. Except it's not, because remember, these don't correspond to the letters of the alphabet. They have to be between 0 and 25. So now I have to take all these answers and mod them, mod 26. Same process as before. So we do n is equal to q times m plus r. M is going to be my mod, which is 26. This is going to be my values of n. This is going to be 105 for the first one. It's going to be q times 26 plus r. So I need to find, this has to be less than this, remember. So I need to find a value for q such that this value will get as close to 105 as I can, but not go over it. So how I do this is I divide 105 by 26 right here. That's a 26. This will give me 4.03. So 4 is my value. This whole number right here is my value for q. So 4 times 26. So 105 is equal to 4 times 26 plus r. This is equal to 104 plus r. That means r is going to equal 1. Okay, so this is going to be equal to 1 mod 26. So this is the numerical value you're getting out of that. And we'll have to repeat this process for the rest of them. I'll just go ahead and fast forward through that and do it, and then you'll see what I'm going to get, okay? Okay, so I did all that for the rest of them, and here are the answers I got. So this is my plain text. I decrypted the message. We just have to convert these letters. So these are my x values. We're talking about x values here for each one of these. And we're going back to the domain. So this is going to be 117.403. So I'll look at my chart again. 117.403. 1 was A, which is B rather. 1 is a B. 17 is an R. 4 is an E. 0 is an A. And 3 is a D. So what I decrypted is the message bread, which is the same message that I started with. Okay, so that's how you do that. I figured it out. So there you go. So this is what happens when you encrypt it. You get this message right here. And then when you decrypt it, it goes back to being bread. So that's how the Affine Cipher works. Hopefully that was useful. And thank you for watching that.